Yeah, any questions? So we have a formula for we have a formula for the number of points in the finite field of size q raised to n on the given curve. So the formula is difference from the projective line, which in that case will be q raised to n plus 1 size, many points. Difference with that is given exactly by this sigma alpha I to the n, where alpha I are the 2g roots of the complex roots of the L function. So if once we show that each of these have norm square root q, we'll get the error term to be very small. It's square root of the main term. Okay, so we do some reductions before proving the Riemann hypothesis. So one is obviously this base change, that Riemann hypothesis is true for a curve defined over finite field fq, if and only if it is true for any higher field. So changing the field will not change the truth or falsehood of the hypothesis, Riemann hypothesis. Second reduction, which is based on the first reduction, is about the counting. So as long as we know that the difference with the projective line of size q raised to d, as long as we know that it is bounded by some, let's say, multiple of q raised to d by 2, where multiple should not, b should not depend on, a and b should not depend on q or d. So what can it depend on? It can only depend on the representation of the curve. So curve was given to you via some polynomial or system of polynomials. So in that a and b can depend, but they should not depend as we change q and d. So if such a estimate is available, then again it will imply that Riemann hypothesis is true. It's if and only if. It's had an interesting proof via convergence of infinite series. And the last reduction, most important reduction, is to Galois cover. So this is inspired mainly by splitting fields which appear in Galois theory. So the key example is, if you take this elliptic curve x2 cube minus x2 minus x1 square, so think of x1 as fixed to some constant, so then this is a cubic, but when you quotient by the cubic, you only get one root. Usually you don't get all three roots. So you want to go to a field where all three roots are present. That's called the splitting field, and it's unique. The minimal splitting field is actually unique over kx1, and that again will be transcendence degree 1 field, so we can think of it as a curve, and that curve is where we'll try to prove Riemann hypothesis. Yes, so there are kind of 4 fields. One is the field of constants k, small k, other is small k x1, that's the transcendental field. Then over that we have algebraic extensions. So big K is the function field of the curve, and big K prime will be its Galois cover. Both these top extensions, they are Galois extensions, which means that if you write down any polynomial with coefficients coming from small k x1, if it has a root in k prime, it has all the roots. If you write an irreducible polynomial, so any irreducible polynomial which has one root in k prime has all roots in k prime. So that is called normality. It's not very important here. but it kind of tells you why we are there. Yeah, at the level of, so the geometry is over the projective line, which is basically kx1. We have a covering by our given curve, and we have constructed a new cover C prime there. So such that what happens? I just finished the revision. Do you have any question? So we are at Galois cover. So what is happening is we have the projective line which we covered by the given curve, which means basically that any point P0 here, if you look at its, let's say, second, you just project it to one of the coordinates, and that will be a, obviously it will be a point in on the projective line. So usually we take it to be x1. So P0's first coordinate, when you project P0 to the first coordinate, then you get a point on the projective line. And the second coordinate x2, that has at least one value is present. The other values may or may not be present. So in the case of elliptic curve, there are three possible values of x2. Maybe only one is present. So to get the other values, we go to the cover C prime, where you will see all the missing x2 coordinates. So this is the new thing that we have done.
I have a question. When we do take a Galois cover first from, suppose this extension of C, right? So is that the primitive element, like, can we write it something like k of alpha of x1? That
Yes, yes.
So basically, just by changing the base field,
Yes.
from fq to some fq raised to k, we'll find the splitting field.
With fq raised,
Kx,
you are changing the finite field.
like that, like the degree extension can be.
No. It's not. It's actually, this discussion is nothing to do with the finite field. So small k could have been complex also. This is a field independent, base field independent discussion.
Understood. Okay.
Because it's happening, because the thing is happening over x1, which is a transcendental field. So it's more a property of the transcendental field, and where, what algebraic extension of that are you going to?
So this k prime will be some k x1 of some alpha.
Yeah, where alpha is a functional thing, it's not a constant.
We can't write it as a k of alpha
No, it's
prime of x1 type.
No, yeah, it's impossible because x1 is a parameter. So whatever alpha is, it's a parameter, it's based on the parameter x1. So if you fixed x1, then alpha will become a constant, but by itself it can just be x2. So this is more complicated, and it's different from the traditional Galois theory which you study in one or two courses actually. They don't discuss this case, although the theory applies, because you can take kx1 as your base field, and then over that everything is algebraic and finite. So it's, but it has an additional interpretation that Galois theory is not aware of. The additional interpretation is that here actually we are covering curves. So the curve, basically any point in P1 was covered by few points P0s, and a point P0 is being covered by few points in C prime, where it cannot be covered any further. So P0, whatever possibility of points is, P0, P1, P2, these we have now available.
One more question. Suppose I let take over from finite field now. Just by changing a base field to some higher field, can it always split? Can we do something like that? FQ, can I go to some FQ raised to k?
Yeah, you go to FQ bar.
Okay. But still we won't be, like, this will still not possible, right? It won't
Not
be
possible, yeah, because of the same reason which I said, that it's because of x1. it's not because of, I mean, you can take small k to be complex. The problem will not go away. So it's not an issue with FQ or FQ bar or complex. Okay, and the function field part you can think of like this. So kx1 was the function field for the projective line. So this is embedded in, it's a subfield of kx1 x2 mod the ideal that defines your curve, given curve, and this will be a subfield of a bigger field. So for example, this over x2 we have also added y2. Both x2 and y2 are algebraically dependent on x1 because everywhere transcendence degree remains 1. So x2, y2, they cannot be independent. They both are actually dependent on x1. I mean the three elements x1, x2, y2, the transcendence degree is exactly 1. And the ideal will have now new relations defining y2. So that's so the arrows are expected. I mean, you know that the arrows will be opposite. So the curve covers the projective line, but the function field is a subfield. The function field of the curve is actually a superfield, that of the line. So this is by containment. And the ones above, I mean the ones on the curve side are projection. So let me just give a concrete example here. So you started with this elliptic curve. So this gives you x2, but you need other 2 points also. So for that, what you can do is introduce this y2. Right, so x2 is a point corresponding to the second coordinate corresponding to x1, and y2 is also a second coordinate corresponding to x1. You also want to embed the condition here that y2 is different from x2. So for that, I can just divide this by y2 minus x2. Okay, so for example, this means that for x1, x2 was obtained, and then a second, so point P1 via y2 was obtained, and point P2 will then be implied because, sorry, this it's not square, it's cube. Yeah, so the cubic divided by linear will give you quadratic. So quadratic, once you have one root, you also have the second root. So you get the 3 roots. So those are the points. So P0 is the point x1, x2. P2 is the point, P1 is the point x1, y2. And P3 is the point, P2 is the point x1. So this would be, you want y2 prime from here. I guess you look at the first equation. So the first equation, coefficient of x2 square is 0, right? So which means that once you have x2, y2, you sum it up and take the negation. Those are the 3 points. Okay, so this ideal, keeping x1 kind of fixed, you get all values of x2 in the curve C prime.
How did this third point come? I'm not clear. Minus x2 minus y2.
Oh, this is just look at the first equation of the elliptic curve. So if you have two values of x2, the third has to be negative of the sum,
Okay.
because their sum is 0.
Yeah.
So these are the three roots for x2 given x1. This is how you can think about this explicitly. And yeah, so I write this because it's a bit important to now see the connection between these three with respect to the automorphism, the Galois automorphism. So let F be the Frobenius with respect to base field, which is Q, size Q, and sigma be the Galois automorphism of Kc prime, the biggest function field of the curve, over Kx1. Okay, so what sigma, well, what Frobenius does is clear. Frobenius simply will just raise x1, x2 to qth powers, because that again is the root of on the curve. And what the Galois automorphism will do is it will fix x1, because x1 sits in the base field here, base function field, and it will then has to move x2, right? So how will it move it? So P1, well, first of all, it will not move x1, x2 point, because that point is in the okay, I should have said, yeah, not the line. I should say the previous curve. So yeah, so in this case, it will not move x1 comma x2. So it will move P1 to where? So P0 it will not move, but then the only place where it can move P1 to, because P1 has to be moved to, I mean, x1 will remain fixed, so y2 has to be moved, but then y2 has to move to a conjugate root. The only option is P2. So that's the important thing to remember. So the Galois automorphism is just swapping P1 and P2, fixing P0. And what is the action of Frobenius? What's happening with P0? Yeah, actually it's hard to say anything here. Because x1, x2 I am using variables here, so this will be tricky. I cannot make a statement here. I can only give an example. So if suppose x1, x2 you fix in the base field, then the Frobenius action will be clear, right? So Frobenius on P0 will not move it. So P0 will not be moved by the Frobenius because we have picked x1, x2 to be point in the base field. P1 and P2 generally will not be in the base field. Why is that? Well, because when you fix x1, the cubic may have one root in fq, but the other two may be in fq square. So in that case, then Frobenius will also swap these 2 points. So I can just make a kind of a generic statement, but not a general statement, because it will depend on how you have fixed x1, x2. But usually what will happen is Frobenius will just fix this point which is in the base field, and the other 2 points it will just swap. Okay, so this example is showing you that the Galois automorphism, which is acting on the function field, kind of behaves very, in a related way with the Frobenius. And this is what we'll use now. Because Frobenius is defined also on functional x1, x2, because we'll just define it to be mapping x1 to x1 to the q, which will be for the function x1. You don't have to fix x1 to a.
This one not clear. F P1 is P2 usually also like f of P1 is x1 comma y to the power q, and f of P2 is x1 comma y.
Yeah, but we are looking at a point. The x1, x2 is something fixed.
Yeah, I'm fixing it also. Then x1, x2 in the base field. So x1 to the power q is x1 again. Y to the f of P1 is x1 comma y to the power q,
Mm-hmm.
and f of P2 is x1 how are they equal? Y to the power q is equal to minus x2 minus y2.
Oh, how are they? Well, yeah. So that has to be explained. Such that x2 cube minus x2 minus x1 has only one root in fq square. The other two roots, then they will lie in fq square, or we can be even more specific. So x1 is already in fq, the other one will lie in fq square, the x2 coordinate. Right? We can fix x2 cube minus x2 minus x1 is an absolutely irreducible polynomial, so we can just randomly fix x1 from fq and hope that x2 cube minus x2 minus that has one root, not all the roots. So in that case, I want to study the Frobenius. So in that case, what I had written is true, that Frobenius will be fixing P0 and it will be flipping P1 to P2. Okay, this is the action of Frobenius. Is that clear now?
So the function field of C prime is basically, if I fix x1, x2, then it will always be equivalent to fq square or something like that, saying that, right?
Yeah, I mean, I think you cannot see it through the function field. Function field, you can only see Galois automorphism. What I'm saying here, for this you just focus on the equation x2 cube minus x2 minus x1. So there we are in the case where when we fix x1, it splits into a linear factor and a quadratic irreducible. Now for the quadratic irreducible, the roots are conjugates under Frobenius. That's all. That's all what we are saying. So they are conjugates in FQ square via F. Conjugates over FQ square via the Frobenius. Yeah, so since we will be intimately using these two actions, it will be good to remember this picture, how the Galois automorphism acts and how the Frobenius acts on base points but also on functional points. So there are multiple actions going on in different domains. Yeah, one more thing is needed to be pointed out, that is, can P1 and P2 be equal? So you fixed x1 and then this x2 cube minus x2 minus x1, it has it has a repeating root for x2, right? So when that happens, I mean, by basic algebra, you can actually show that there are very few x1s for which it is possible. In particular, you can show that x1 is a root of the resultant with respect to x2 of f x1 x2 and its derivative. Okay, so it is something to do with f and f prime. So when you fix x1, what happens is that this f actually becomes a square full polynomial. So it's linear times square, say. So when you differentiate it, this repeating root actually divides both f and f prime, and the resultant will take care of this. So when you eliminate x2, you basically get a univariate in x1 whose roots or whose zeros are exactly characterizing this situation. It's if and only if. Okay, so these are the bad x1s, but they are very few, because the geometric intuition is that you are in a one-dimensional variety, which is basically your curve. So how many singular points are there? So those singular points are always finite, because you intersect the curve with its derivative, dimension becomes 0. So these are very few. Thus P1 equal to P2 happens for less than equal to degree of f square many x1s. Okay, resultant has degree around square, it's actually smaller than square. but the point is that it's a finite number. So again, generically speaking, or usually when you fix x1, the points you get, they are always different. The conjugates are different. So this will also be useful to remember.
Smaller field, it can be a problem, right? Because
Yeah. So, but so that will be another reduction that will prove Riemann hypothesis on a big field. In fact, that's why we gave this reduction, because we'll actually do that. How big the field should be, that we will soon see. So let's define the Galois group, a notation for the Galois group. Be the group of K automorphisms Okay, so this is just formalizing that picture. The top field is Kc prime, and the middle field for the curve, function field for the curve, is Kc. So look at the automorphisms which fix your given function field and move the Galois cover. Okay, so you can see, I mean, this is again the standard group automorphism. It is a group, and its size is actually equal to the degree of this extension. So that we can state as a proposition. And let C prime be a Galois cover. Then the size of the Galois group is equal to simply this, as expected. Yeah, so if you have already seen Galois theory, it's a trivial statement. If you haven't seen, then the idea is that you just, so Kc prime over Kc is a Galois extension. So you can, by primitive element theorem, you can write this, I think that is what you were saying before. So there exists an alpha such that Kc prime is just Kc with this alpha attached by primitive element theorem. And which means that the min poly of this element alpha, its degree is exactly equal to the degree of the field extension. This you can do always. This does not require Galois extension. This is just a property of finite algebraic extensions or finite extensions. The place where Galois theory comes is for the min poly of alpha. There are these many conjugates, and they are all present in Kc prime. When min poly gets actually it is splitting in Kc prime. In fact, something even stronger. Kc prime is the splitting field. And so has all its conjugates. So to classify the automorphisms, you just have to map alpha to a conjugate, and the number of conjugates is equal to the degree. So you get all the automorphisms. Which is equal to the degree. So it's a simple proof, it's a standard proof. This is how you start Galois theory anyways. So all these conjugates are present and they are exactly given by the degree of the splitting field over the base field that you are always fixing by these automorphisms. Right. So with that, yes, so we have the action of these automorphisms on the curve points. Yeah, so this is it's an automorphism of the function field. Do you see that its action can also be done on the points of the curve? Can be seen to act on points P in C prime. Why is that? Well, it's simple. So this whatever
The rational function, we can separate out the zeros and poles. So when you apply the automorphism, the zeros and poles will go to their conjugates.
Right. Yeah, so just like you had this x1 comma x2, sigma will be mapping x1 and x2 to some functions. And the idea is just simple, you use that function also on points. So I give you two coordinates, use the same function as defined by sigma. So yeah, so it says both the things. Sigma can be seen to act on points P prime in C prime via its action on the functions, because so sigma x1 and sigma x2 are can be seen as functions in Kc prime. So use them to define sigma p prime. That's all. The usual thing. Yeah, now what Dipujit was saying, that sigma x1, since it's a rational function, it may have poles. So what will you do with the, when this point p prime is a pole of those functions, then you cannot evaluate sigma x1, no? That would be a problem. So what do you do there? Yeah, so that will also get automatically resolved, but let me not think about that here.
Sigma x1 is always x1, right?
Sigma x1 is?
X1 only always. So x1 is in Kc.
No, sigma is some arbitrary automorphism of the function field.
And every element.
Yeah, okay, you are saying, okay, in the case when, yeah, when,
Is every element of Kc prime?
no, both x1 and x2 may be moving.
And every element Kc prime is a polynomial in the primitive element, right?
Yeah, but we are not talking about any explicit representation. So C may be given by, so I think you are getting confused with the representation for the projective line. There we use kx1.
This x1 can also be in Kc prime.
That is true. Yeah. So in that representation, actually x1 is fixed. But then sigma x2 has the same problem. Sigma x2 is it has to move. If sigma is non-trivial automorphism, then sigma x2 will be non-trivial. So it's a rational function. How will you evaluate it?
Right, sigma will take some there, right? Because it's an automorphism. What's the problem? I'm not seeing it. Sigma x1 will belong to some point in.
The problem will be when you fix x2 in the base field, constants.
That will be part of Kc, and that will be fixed only.
No, say you fix it from fq bar, an actual point. Basically, sigma x2 has some poles. So let's just look at the image of sigma on that pole.
The thing is, x1, x2 are always in Kc prime.
Mm-hmm.
So sigma x1, x2 are always defined, right?
Yeah, functionally yes. But on actual points?
Actual point.
Yeah, so let me not get into this. Anyways, the poles will be few. They will be finitely many. So it's only a problem for finitely many points. For all the other infinitely many points, you have action of sigma on them. So that should be good enough, I think. Second is Frobenius. What is Frobenius for functions and points? So Frobenius f at the level of functions will map f to the q. Okay, it's simple. It's always defined. I mean, it's defined for all the functions. You just exponentiate. And on points, it will map alpha beta to what? So for technical reasons, it will map by q prime, q inverse. Okay, so on polynomials it is what you expect, and on points it is it's like exponentiating by q, but except you are doing it q inverse, which is another kind of Frobenius. So for example, if alpha was sitting in fq square, then alpha q inverse is actually the same as alpha q. And if alpha was sitting in f q cube, then q inverse is basically q square. So this is just a repeated application of f, all the way except the last one.
In the previous part, we see the curve by its coordinate ring, right? The explanation always in coordinate ring, right? We see the curve through its coordinate ring.
I mean, the curve is given to you. I mean, in our theory, it is given to you just by a transcendence degree 1 function field.
I mean, generally exponential are from the coordinate ring, right? And there is no problem of poles.
No. So coordinate ring, yeah, coordinate ring will always, by definition, have x1, x2. But the problem is, what is sigma x2?
And the way is like we take points from the coordinate ring. Now KC is just an extension of that, right?
Yes.
The points in the curve are always the coordinate ring.
So are you saying that there is no pole?
Yeah, well, yeah, that would be like
True.
curve.
I think you have proved that. Yeah. So there are no poles. There are no poles except obviously in the projective case you have the point at infinity. That's always there. That's there for all polynomials, point at infinity. But yeah, other than that there is. So point at infinity has to be mapped to itself. Sigma infinity is infinity, but other points are well defined. Yeah, so that's the answer for this question. Okay, good. So you just define sigma infinity to be infinity, because that's not an actual point. Everything else you will have definitions. Yeah, although explicitly I don't see why when you go to Galois field extension you will only get polynomials. I guess in this example, yeah, you are getting, of course. So for example, how will you map, yeah, in this example you can see that. So y2 is being mapped to minus x2 minus y2. And ultimately you can reduce everything to the primitive element, theta or what alpha we said. Yes, so I think that should be fine, but still I'm not formalizing that part here. Okay, so yeah, we have defined sigma everywhere and Frobenius everywhere now. Yeah, one easy property here is that Frobenius is injective. right? Since it is just exponentiating, it cannot send non-zero to 0. That's a special property of Frobenius. So it's a K monomorphism. It fixes FQ. This is what I'm saying. It fixes FQ, and anything else it cannot send to 0.
Monomorphism just means an injective morphism. Right?
Yeah. And it is fixing K. Yeah, maybe an example will be enlightening. So the Frobenius, suppose you have this ideal x1 minus alpha, right? So Frobenius will map it to so ideals, in this case I've taken a principal ideal because you'll see the concept already. So Frobenius will map this polynomial to just at the level of ideal. Is this correct? Yeah, maybe not ideal. Let me just talk about the polynomial. Yeah, so by definition it maps this polynomial to its qth power, which comes out to be x1 q minus alpha. No, this is not good. I wanted to give an explanation why for the point alpha beta it's like this.
Right, f to the power q is f of x to the power q, like that, and every that will map that power. Then at ideal will be equal.
Sorry?
When you do f to the power q, like this x, the transcendental element will just go to the power q always. F to the
Mhm.
raised power q. In that way the ideals will be equal.
No, but I wanted to say something about the 0. Now the 0 here seems to be
Alpha
unchanged. It remains alpha.
Alpha to 1 by 2.
Yeah, but the thing is, if alpha is in FQ, then it's alpha to the 1 by q is equal to alpha. Yeah, so okay, I don't get an explanation for why I did that for the point. But if you look at the order of alpha, the 0 alpha, so this under the Frobenius, it blows up by q. Okay, so essentially the valuation under the Frobenius gets multiplied by q. So at least this much we can observe. Let's see. Yeah, I think that this at the level of point it should be this, but we have to recheck this when we go to the proof of Riemann hypothesis. And of course the k points on C are exactly the points which are fixed by the Frobenius. Right, this is clear. This is why we work with Frobenius, because the points that we want to count, they are basically the fixed points of this morphism. Okay, so with that setting, now what I want to do is I want to relate the count of points on C prime with C, because I want a true reduction. So it should not happen that C had some number of points and in C prime there is a totally unrelated number of points. Right, then we can't do Riemann hypothesis by going to C prime. So for that, what we have to see is basically how a point P in C gets covered by points in C prime. Right, we have to focus on that cover picture. So which is algebraically you have to do this. So for a Galois automorphism, fixing the function field of the curve C, define n1 C prime sigma to be those points in C prime such that sigma inverse Fp is equal to P. Okay, so what this is saying is that when you apply Frobenius on this point, you get a conjugate of the same point. So Fp is equal to sigma P. Right. So why are we doing this? Because as we saw in those explicit examples also, the points which cover your base point, when you apply Frobenius on them, you may not get itself, you may get a conjugate, right? So this is basically counting that. What are the points for which Frobenius gives a conjugate? And here conjugate is by sigma. And N1C N1C is realized as just N1C1 or identity, right? So the number of k points on the curve which we are interested in, it is just take sigma to be identity or 1. That's the notation. Okay, so now we can give the connection. So sigma, if you let me think of this as averaging. Okay, so what we will show is that N1C is the average over all sigmas. Plus order 1. Order 1 means it's not an absolute constant, it's a constant dependent on delta. Let me write this properly then. Okay, so N1C is basically the average over these points in C prime under sigma. You count each of these, take the average, that will come out to the number you want, which is N1C. With some error, the error is essentially a constant. It just depends on the degree of definition of the curve C.
N1C is the number of fixed points of C.
Yeah. So it's the thing that we are interested in. The given curve was C, and you want to find its FQ points, count its FQ points. So this is the relationship. When you go above, you have to basically do averaging with respect to the automorphism group. And it has a really simple proof based on the setting that we have. It's quite easy. What you have to do is you just have to observe that a point on LHS, in the RHS it will have G many points that cover it. So basically in the LHS it is counted once, in the RHS it is counted G times, and then you average, you get 1. Okay, so the counting matches on both sides, except for the points for which what may happen is in the cover in C prime, the conjugates are equal, they may not be distinct. So that is a problem, right? If a point P is covered by its conjugates in C prime where the conjugates are repeated.
But it is a Galois extension, right?
No, so yeah, so that needs some care, right? Because in the example also, once you fix x1, there was the resultant argument.
So it might not, after fixing, it might not stay
Exactly.
Galois.
It's not that, so we want to count actual points. So it's not true that for an actual point in the cover you have distinct conjugates, because there are some bad actual points. Why are they bad? Why do they exist? So they exist because of this. You look at x2 cube minus x2 minus x1. So you can set x1 to something I think in this elliptic curve case you cannot, but in general you can set x1 to something so that the polynomial is squareful. That can happen. I mean, a silly example, it will not work, but just to show where the algebra will fail. Suppose you have x2 cube minus 1 minus x1. So there if you set x1 to minus 1, then you get x2 cube, which is squareful. Right? So there might be exceptional x1. So these are the exceptional actual points where the covering picture is not generic. It's somehow a bad case. But for that we'll use the resultant argument. We have stated here in blue that the x1s for which two conjugates in the cover are equal, they are very few. So they are actually, for us, they are constantly many, because degree of f we are considering as something constant. So just from that it will follow. So that's the error term. Everything else is nice. So let phi be the Galois cover. So for a point P in C, let the distinct points in C prime above P be phi inverse P. So pre-image of P are these points which are kind of covering your point, base point. So let's call them Q1 to QR.
So what is phi with C prime and Galois? What is phi? This is morphism or something?
Yeah, so phi,
Phi is again power.
I mean, you can understand it by the opposite arrow at the level of algebra.
Yeah, it is a morphism.
It's a morphism. Why is it a morphism? So what is the morphism? It's actually the function field Kc. It's embedded in Kc prime. So that embedding is the
Okay.
morphism. So you have to see the opposite. Yeah, which is why I gave the,
In geometry, there was a relation that if something covers a point, you have morphism from E to B when the function field is mapped in the equal direction. From that you can see.
yeah, it's this arrow, the top one going from Kc to Kc prime, that's phi. At the level of algebra, it's an embedding. For the function fields, it's an embedding. For the curve C prime to C, it's exactly the thing which is happening in the picture, that for P0, what are the conjugates? They will be mapped, all of them will be mapped to P0. Yeah, so there is no, I mean, at the level of points, it's not a very good looking map. So you should actually think of the embedding. Yeah, it's projection. Yeah, it was projection when you went from C to P1, but from C prime to C, it's not clear what it is. It's not really a projection, because P1 is the point x1 comma y2. You are mapping that to x1 x2. So why are you mapping y2 to x2? Yeah, that's not actually happening. You are not mapping the function phi2 to x2. You are only mapping the point P1 to P0. Yeah, which is why I drew that picture. So it's very explicit what we are doing. And we can now talk about the pre-image of the base point P. So Q1 to QR are those. What can you say about R? So, well, we can make, okay, first we can observe that so what can you say about f of Qi? What is the Frobenius action on Qi? These are actual points, so Frobenius will just permute them. So this is again in phi, a pre-image of P. That's one thing. The other thing is R, the number of pre-images. Yeah, it cannot be more than the Galois group. But R can be anything smaller also, right? There is no reason why it will be exactly equal to Galois group. In some exceptionally bad P's, it can be just 1, because what is happening is all the conjugates above it are equal to P0, equal to P. Those things are not ruled out. Okay, so why is R less than G? That is what we should ask. It happens only when P has repeated conjugates. That is, P ramifies. Okay, so ramification is the hurdle here. But we have seen before that such points are less than equal to delta square, which we are thinking of as constant. Okay, so there are only constantly many ramified points. Everything else, R is equal to G. So that's all. So for unramified point P, and unramified K point, sorry. On the curve C, what can I say? Yeah, so this phi inverse P, which is the number of Q in which is the Q's such that this number is R, is G. So all these things are equal. Okay, for an unramified K point on the curve C, the points which are above P in the cover, that's R. In fact, let's just put that. That's equal to those points. In fact, this I think I can say C prime. That's the point. It's actually equal to all those points in the cover which are fixed by sigma inverse F for some sigma. Right, and this is this will be equal to G. So which is just saying that in the proposition statement, that point Q will be counted in one of these summands, N1 C prime comma sigma. Not one, yeah, so it will be there will be these many counts. In fact, there will be G many counts. For the point P, there will be Q1, Q2 dot dot Qg. So overall, in the average, it will be counted exactly once. I think one more observation has to be made, which is if there is a point Q that satisfies FQ is equal to sigma Q, then what can you say about its what can you say about phi Q? Then it means that phi of FQ, phi of sigma Q, and then you can swap this, which will be equal to phi Q, because phi Q is in the base field now. So sigma will fix it. So which is basically saying that yeah, but do I need that? This is trivial. I think what I need is something like this. This is correct, right? So any point Q which is being counted in some n1 C prime sigma, that has to be in the preimage of P. No, wait.
The definition also earlier is given should be sigma inverse of FQ is P, right?
Yeah, sorry. Wait, what?
R is equal to the next page.
Mm-hmm.
And the next page. We wrote R is equal to phi inverse P. Definition sigma inverse of FQ is P, right?
Not P. It is saying that sigma and F acts in the same way.
Yeah, no, that is correct. That is for that's in the cover, right? So there you have to talk about sigma inverse F. No, I think this is the set condition is enough. This says everything. Just this one small observation is needed, that if Q prime in C prime satisfies then phi of Q prime will be in the curve C. This is the only thing I need, I guess. I mean, you have to look both ways. So take a base point P in C. How many covering points are there? That's given by the first equation. But you also have to see that points which I am counting in C prime, which are fixed points of sigma inverse F for some sigma. Then its image under phi is a k point in the curve. That is true because you just apply phi on that identity and sigma will go away. So you will get that f of phi q prime is equal to phi q prime, which will say that phi q prime is a point, k point in the curve. That's also now we have seen both ways. So now sigma n1 c prime sigma, small sigma, covers everything correctly.
And still not clear, like, how did P come into picture there? Like, would all Q belong to C prime? Is that just F and sigma?
Oh, P is just
The definition of phi inverse, that phi inverse P did not even come in the picture in the next page.
in the next page.
And this in that
No, no.
did not even come in the
In the next page, it is talking. We are making a statement about the cover of unramified points.
like for any point, like for fixed point P, right?
Yeah, which is unramified.
Yeah, so should it Q belong to C prime or phi inverse P? Like not, yeah, how's P even coming into the picture?
Oh, in the set.
P not coming into the picture.
No. Yeah. So that should be. We can edit that.
And also Q goes to
It's in it's in C prime intersection preimage. That is what was meant. It's the Q's which are in C prime covering the point P. That's fine. But if you look at some random Q prime in C prime, which is being counted in N1 C prime, then it does correspond to some key point on the base curve. That's also true. Yeah, so with these two, I think we are now set. So thus Q, any Q in C prime, any Q in C, any P in C contributing to I think this should be said about Q prime in C prime. So any Q prime in C prime contributing to this sum either has phi Q prime ramified or has phi Q prime unramified. Right, these are the only two cases, and both these images, they are in the curve C, K point in C. So which means that
What is the statement I can't understand? Like also Q prime belong to C prime? What does it imply? I'm not clear.
oh, let's just remove also. Let's write this properly. So if Q prime in C prime satisfies this, then this happens.
C K means it's a K point.
It's a K point here. It's saying that any fixed point of sigma inverse f, when you quote unquote project down, it's a K point. That's all. Note that it's obviously true if Q prime was a fixed point of f, because if it's a fixed point of f, then it's then clearly it has to be a K point. It's a K point of C prime, and you project down, it will remain a K point of C. But it's not just Frobenius, we are also putting sigma inverse. So there is some content here. It is saying that even with sigma inverse, Frobenius actually does its job and it gives you a K point. That can be shown just by applying phi both sides. Then sigma inverse goes away.
For a general Q prime summation, AI is times the primitive element, and we applied this F. So alpha to alpha, then taking goes to a conjugate. Okay. Alpha to alpha goes to.
It might be easier to apply phi on fq prime and sigma q prime. So phi on fq prime will, you can swap phi and f, and phi on sigma q prime you can swap sigma and phi. Yeah, so with the top two properties, you have now that phi q prime is, you are getting points in C and yeah, both are in C. I mean, either it's this point, k point in C is ramified or it's unramified, and the ramified cases are very few. So the unramified cases will give you G times the number of points, while the ramified cases will be very few. They'll just be constant. In fact, technically I can multiply this with G. I should multiply this with G. But then the Galois group size is also just degree. So ultimately this finishes the proof.